Hello, so welcome back to C3660. So this is lecture 11. This is lecture 11 on the topic of soil shear strength. This is Dr. Kwan from Cal State Los Angeles. So before we start the technical topic, let's talk about K history. In 1913 at Canada, Winnipeg, there's a famous K history that the structure is for grain storage. When the grain start to import to this structure, it happens that the loading become too large that the soil can handle, and end up the whole building collapse in a way that the structure is sound and intact, but the soil fell, which means there's a soil bearing capacity failure at the foundations. So end up the whole structure tip over. And there's an engine drawing how the structure rotate when the soil capacity cannot handle the structural load anymore. And this is drawings, so identifying the critical slip surface. So as the soil fell, a circular slip surface will happen, so which indicated on this slide on the blue circles right there. So the topic of the soil shear strength is critical as a simple case history that we see. If we go back to civil engineering case history library, you see many of them is about the foundation failure, which is the case that the soil strength cannot handle the structural load. So it's not a structural problem, but it's a geotechnical engineering problems that highly rely on the characterizations of the soil strength. So we want to know about the soil strength, but what soil strength depends on. It depends on highly depends on the soil types, because like sand, we know is this from back to lecture number 1. Remember that we talk about sand, where it comes from. This is from the physical breakdown or physical decompositions of the outcrop, which results in a lot of particles that have frictions with it. So the strength from the sand comes from frictions. On the other hand, for clay, it highly depends on the chemical compositions of the clay minerals, which result in cohesions holding the clay particles together. So when we talk about the strength of the clay, we mainly look at the cohesions. Also, like soil density matter, the stress history matters. So we learn about the third semester. We also talk about this in the topic of soil consolidations, when that's the maximum pass pressure that we can characterize. So which means like we can find out the effect of the stress history on soil strength theory, which is also important factors. Also, geological settings, geology, the sites also play important factors when it comes to the topic of soil strength. Also, last but not least, the loading mechanisms also matters. So, for example, is a picture showing like a lot of different type of geotech structure or foundations that relate to soil strength. So, for example, on the left-hand corner, we have the embankments. So what we find here is the embankment give a circular slip surface, same as this floating wall. So when all this structure fell, also like a shelf and also a spare foundation, so it's a T shape over here. So all this like a foundations or earth structure, when they fell, will create a critical slip surface. And along this critical slip surface, it will provide different type of loading mechanisms on the soil. At the bottom, it provides the simple shear motions, pretty much like you can imagine the soil elements that the slip surface that cut through. You have a top and bottom part, so it becomes like a shear mechanisms. So same as on the wall and also on the foundations, the bottom part of the slip surface is kind of like a shear loading mechanisms. And on the upper sides and the lower sides of the shear surface related to the structure, you will, on the upper side, you have right underneath the foundations or loading area, then you will find there's a compression type of loading, and the other the other side you have a tension type of loading. So there's three different type of loading mechanisms in engineering design, particularly in geotechnical engineering, when we design for the foundations of earth structure. So with all this in mind, all these different factors, the soil strength characterization is very critical for civil engineering project. It's become like a daily routine in our business of practice. Such that, like to do that, we conduct lab or field testing. Those are very important for us to understand the topic of soil strength. So for the limited time that we have for this lecture, we only focus on lab testing of soil, which help us to understand the topic of soil strength. Speaking of loading, the different type of lab testing that we have on soil strength. So if we want to characterize like a soil strength, the first thing we need to think of is the loading mechanisms. One more time, like when you have the critical slip surface that we mentioned about, the bottom part of the slip surface, it provides like a shear type of mechanisms, and at the other two ends, right underneath your loading area of foundations, or at the other end of it, which is at the toe of the embankment, for examples, you have extensions type of loading, which give us the loading mechanisms that can be handled by triaxial test. So a triaxial test is like the compression test that you have done for your material mechanical class, where you have a cylinder type of like specimens. You can do either like compressions or tensions type of testing. But in geotechnical engineering, we call it triaxial test, which is a fundamental geotechnical engineering topics in our business, triaxial testing. So within the triaxial testing, there's different types. So understanding all these different types of testing will help us to understand the topic of soil strength, and also helps you to visualize, or helps you to understand how the business of geotechnical engineering to be like a conduct in a daily basis. So different type of testings for triaxial tests. The most simple ones is the unconfined compression test, which we'll cover in this class, and when you're taking the geotechnical lab class, which will be the lab exercise that you'll be working on too. And we take the soft forms, we call this to be UC test. We take these, the first two letters of the unconfined compression test. The next level of triaxial testing is the one that is being confined. So unconfined compressions, the unconfined means there's no like a horizontal stress, sigma 3 adding on the soil specimens. We talk about this more when we get into the details of each of the testing. For the next level of testing, we do have a confining stress, sigma 3. The first one is unconsolidated undrained test, the UU test. And in this class, we will also cover this test in details too. So the UC test and UU test, so we call those like to be the undergrad level testing down. We wish our undergrad students can fully understand about these two triaxial tests. And beyond that, the advanced testing, triaxial testing, which require much more complex understandings in the soil mechanics, and we typically cover those two tests in graduate level. So in CalCLA, we talk about these two tests in details. The next level class, which is like 5660, the Geotechnical Engineering 2. And the two tests after that is the CU test and CD test. So they also have the sigma 3, they also have the horizontal confining stress, and on top of that, they will also conduct a consolidation phase, which now make them to be consolidated undrained and consolidated drained tests. So along with those 4 testing, the commonly available triaxial testing. And each test also in our business also come with the cost and the time that need the test to be finished. And the unconfined compression test is the most straightforward, so it's easy to conduct, but you also have its shortcoming. But like it's a quick and a cheap test to be done. And the unconsolidated undrained test is the next level. It's relatively cheap, but the quality of the test cannot be compared with CU and CD tests. Those are very expensive and time-consuming tests, and in return you will get much higher quality test result, which means you will have engine parameters of solid strength that is more reliable. And as engineers, as geotechnical engineers, we need to understand all the limitations, and based on the project, based on your budget, you need to make the decisions on as a project manager or the geotechnical technical expert right there. You need to provide guidance and also provide recommendations, which type of testing you will recommend. So you need to understand each type of testing, knowing the limitations. So those are the 4 different types of triaxial testings. And then we also mentioned about, we have the shear type of testing. And the first one is the direct shear test. We will cover in this lecture. And also when you take the Geotechnical Lab course, there will be another strength type of testing. The students will spend time, the class will spend time on actually working on it. So that is the direct shear test. And it has its own shortcoming of this direct shear test. So when you take the laboratory course, we will discuss the limitations and shortcomings in greater details. And the advanced versions of the direct shear test is the simple shear test. So the simple shear test allows ballast simulations of earthquake engineering. This is the cyclic versions of the simple shear test is the best to model upper propagating shear wave in the lab, which means it's very ideal to mimic assault elements under earthquake loadings. And this is a very hard test to be conducted properly. You rarely find a lab that in the United States that are able to run this step properly. And you come with a great prize when you find someone try to run a simple shear test for a project. So those are the overview of the different type of solid strength lab that being available, and we will start to talk about the unconfined compression tests in better details. So before we talk about the triaxial test, let's look at the direct shear test first. So what is the direct shear test? So a direct shear test is when you have a solid samples like this one, and we want to mimic the shear type of loading. And the solid samples is confined with 2 boxes. Well, a box that has two parts. There's a top part and a bottom part that can slide against each other. So this is the direct shear test. And this direct shear test, before we conduct the test, we can measure the size of the soil samples, the specimen diameters. So we can measure that, and then it gives us the area of the soil samples. And this test has 2 stages. The first stage is the consolidation stage. So after you assemble your soil samples in the box properly, then you will apply a vertical stress. So with the known original specimen height, and also after you apply your consolidation stress on that, so vertical loading, for example, 100 kilopascal, 200 kilopascal. So after you apply the vertical loading, you also monitor the vertical deformations. So we can find out the specimen height after consolidation, because we know the original height, and also we know the vertical deformations because of the consolidation stress then we can find out the specimen height of the consolidations. So this when we like loading the soil samples like vertically, we also keep monitor, right? We keep monitor the deformations. So which means this becomes like kind of like a consolidation test, and end up we can like report, or we can like plot out the settlement curve at the given loading. So we can monitor the settlements with time. So this is the first stage of the direct shear test, consolidation stage. So we typically depends on the soil you're working on. If you work on sand samples, the consolidation stage will only last for minutes, because for sand, it will only take seconds, minutes for the excess pore pressure to expel out in the consolidation stage. So remember, like 2 lectures ago, we talked about the clay primary consolidations. So consolidations is about squeezing out the water from the soil samples. So for example, now when we have the clay samples here, the consolidation stage can take like days or weeks to be finished. So after consolidation stage, which means the excess for water being expelled out at the end of finish the primary consolidations, then we can go on to the shearing stage, which in that case we will apply a constant displacement rate on either the top or the bottom of the box. In this case, so the top box is kind of fixed horizontally, but the top part allows to move like vertically for the consolidations, but during the shearing stage is fixed in horizontal directions for the top part. For the bottom part, now we impose a constant displacement rate on it, and meanwhile we can keep track with the shear displacements, and like we also keep track with the shear the loading that like fell by the soil samples, that is response to the applied constant rate, which means at the end of the day we can come up with a stress strain curve. So we are monitoring the shear load divided by the area, then we can get the shear stress. And with the monitoring shear displacements, we can come up with a stress strain curve of the tested soil samples. So this is the direct shear test. So for the soil strength parameter we need to conduct more than one direct shear test. For the first direct shear test, we subjected it to a certain vertical consolidation stress, let's say sigma 0.1 here, and we conduct the test under the given vertical stress, and we can come up with a stress strain curve. And the stress strain curve that we have the corresponding like a maximum shear stress that we can obtain, and based on the vertical stress sigma 1 now, and also the maximum shear stress that we record, we can find out we can identify that as a delta points on the mole quantum space. Remember from last lecture, when we talk about the mole circles, we have the mole quantum space. So we have our first like a stress point. So and then after that we conduct our second test, and then for second test we subject the soil samples into like a different soil samples, but the same soil type that we want to find out the strength parameters for. So we subject that to a different level of vertical effective stress. Let's say call that to be sigma 2 here. So we will do the test again. We will do the second test, and also we will find out another maximum shear stress under the vertical stress of sigma 2. So knowing sigma 2 and also find out the maximum shear stress that corresponding with that, we have our second data point. So also we do the same thing for test number 3, and we also do the same thing for test number 4. So now we have 4 data points on a mole quantum space, and we can feed an envelope on with this like 4 data points. So in reality, we need at least like 3 data points for us to define the straight line, and at least 4 points is recommended, such that like we can have the more quantum failure envelopes, either more quantum space, which is the y-axis. This is the shear stress, and the x-axis is the vertical stress. And with this like a more quantum failure envelopes, we can find out the C point, which is the cohesion of the soils, and the friction angles with the is the phi point. So this with the Triaxial test allow us to characterize the soil strength parameters, the phi points and the phi point, and also the C point. So we need like a more than one test in order to able to characterize a given soil type. So this is the Triaxial test. Next is the unconfined compression test. So which take place for the triaxial samples, with the triaxial samples. So the triaxial samples is a cylinder type of soil specimens. So after you retrieve the soil samples from the site, you will trim it in the shape of a cylinder with diameters to height ratios of about 0.5. So it's kind of like a tall cylinder. And we can measure the initial diameters, and we can also measure the initial specimen height. So this test, the principle is this is what we call the unconfined compression test. So the unconfined means one more time. It means that there's an absence of horizontal stress. So sigma 3 is equal to 0 for this type of testing. So pretty much it's like your concrete test like you just compress the soil samples or concrete samples to failure without the lateral support or lateral pressure that applied to it. So for the this is like a laboratory setup for the a sketch of the laboratory setup of an unconfined compression test. So the we need like these instrumentations of a low cells and also a dial gauge. So when the soil samples is put on the platform right here, the bottom part will rise up as a constant rate. So push against the soil samples to the low cell. So the low cell can pick up the soil resistance because of the constant rate of displacements that you apply at the bottoms. And meanwhile, you also have a dial gauge to monitor the displacements throughout the testings. So a couple parameters that we can calculate based on this test. We will calculate the axial strength, so we can plot the stress strain curve. But like before we plot the stress strain curve, we need to know about the axial strength. So the axial strength will be the deformations which you can pick up from the dial gauge, normalized by the original height of the soil samples. And the area of the soil samples just keep changing because when you keep loading on the samples, the cross sections area become larger and larger. So we need to, per the ASTM standard for this type of testing, the area is corrected with this formula. So we know the original area, which related to the original diameters, and normalize that by the shear strength, 1 minus shear strength divided by 100%. Then that will give us the corrected area. And finally, we can find out the sigma 1. Sigma 1 will be equals to the loading that you pick up from the low cell divided by the corrected area. Then we can find out the axial stress sigma 1. And with that, we can come out with the stress strain curve with the tested soil samples, which is functions. Again, for the stress strain curve, the sigma 1 will be a functions of the axial strain. And with a stress strain curve, we can identify the failure stress, the maximum axial stress of sigma 1 right there. And again, we can observe that sigma 1 is a function of the axial strain. And we need to understand all the triaxial testing on a mole circles, So remember, sigma 1 is a function of the axial strain. So sigma 1, you can have a continuous value of sigma 1, depends on the axial strain. But now we just look at the time slot, just look at one particular stress that we are interested in, which is the failure stress, sigma 1 maximum, which is this one right here. So we just look at this sigma 1 maximum at for our mole circles analysis now. So we know sigma 1 max, which we can measure in the test setups. And also we know sigma 3, because sigma 3 is 0. It's an unconfined compression testing. Unconfined means there's no sigma 3. So knowing sigma 1 max and knowing sigma 3 equals 0. So we have 2 points on the mole circle space on x-axis for the stress, vertical stress, and which means we can form our mole circles. So with this mole circles, the failure stress is, well, before that, let's find the pole for this mole circles. So we know the stress. Remember one more time from the mole circles last lecture, the pole method telling us knowing 3 items: the pole, the stress points, and also the orientations. These 3 items. Knowing 2 of them, you can find out the 3rd one. So now we want to find the pole. So that's why we look into the stress points and also the orientation, which is the plane. The first stress point you can look at is the sigma 1 max. So we know a point, the sigma 1 max. And also we know the orientations, we know the plane, which is the horizontal. The sigma 1 is adding on the horizontal plane on the top on this specimen. So we know the plane and we know the point. So we can find out the pole, which is right here. And we can double check that with another available points and a plane that we have. So another point that we have is sigma 3 equals 0, which is this point right here. And the plane is the vertical plane that sigma 3 add on. So which is this point. So the pole will be all the plane that cut through. So this pole will be the intersections be the sigma 1 and sigma 3 planes. So we know the pole. And the failure stress, the maximum shear stress for the confined compression test will be happen on the maximum point on the y-axis of the mole circles. So this is what we call the maximum shear stress. So with this point and with the pole, we can identify the failure plane. So again, like the pole method, if we know the pole, and we can, and also if we know the stress, then we can find out the orientation, which is the plane. And this plane is at 45 degrees on the mole circle space. So we reconduct the test, so thus we will find a failure stress, a failure plane that happened within the soil samples at an angle of 45 degrees. So same as like our real soil samples, if we test it, we'll find out it fell at a plane of 45 degrees if we have done the test properly. So be very careful when we use the parameters for design. When we look for the maximum shear stress, it is this point right here, the tau max on the y-axis here. Is not the sigma 1 max. It can be quite tempting when you see a stress strain curve. That would you identify the maximum point on a stress strain curve that to be your maximum stress. Be very careful. This is the maximum vertical stress or maximum compressive stress. but this is not the maximum shear stress. So oftentimes, like students or even like the professional engineers, they make these mistakes, and the price for this in practice is quite high, because I think about it, if you misunderstood the sigma 1 max, this point as the maximum shear stress, it can be very dangerous, because on the Mohr circles, you realize if you either mix these 2 points, you will be off by a factor of 2. One is the diameters and one is the radius. So for one more time, for the maximum shear stress is the radius of the Mohr circles. It's not the diameters of the Mohr circles. So don't be misunderstood that when you have a stress strain curve, you can take the maximum points to be the maximum shear stress. You need to conduct a Mohr circles analysis, and you can find out the maximum shear stress. Okay, so the next test that we will talk about is the unconsolidated undrained test. So this test is the one that now we have sigma 3. So it is a confined test with the confining pressure added on to sigma 3. And this test called UU test, unconsolidated undrained test, which means for this type of triaxial testing, there's no unconsolidated stage. And this is the laboratory setup of the apparatus of triaxial setup for conducting unconsolidated undrained tests. So you will find now soil samples is confined by a pressure chamber, and within the chambers is filled up with fluid. So it can be water, it can be oil. So and there's an outlet for this a triaxial cell, or with a chamber on it, and you can apply the cell pressure. So you can apply air pressure to your cell to try to pressurize the whole testing chamber, which with that applying the cell pressure right here, so you're providing the sigma 3 to the soil samples, both laterally, horizontally, and vertically. Pretty much just like a bomb, like a pressure bomb inside. You apply a pressure all along your soil samples, and the soil samples is isolated. The soil sample is isolated with the outside fluid with a latex membrane. So when you apply a pressure, so when you pressurize the whole thing, the fluid will kind of push on the membrane or the caps, such that the soil is feeling the lateral stress, which is the confining stress. And more details on this a laboratory setup. There's also connections of the soils to an outside pressure source. So this is kind of the pore pressure. So you can apply pressure into the soil, and also we can monitor the water being expelled out from the soil. So there's a volumetric change connected to the soils that if the water comes in and come out from the soils, then you can also collect it. And you will have you also have there's a piece of pore stones right there to block the soil being come out. So when the whole thing being pressurized, the pore water trapped in the soils can only escape, but not the soils, through this channel here. And we collect the water that's come out. So this is the laboratory setup for the triaxial test. And for UU tests, pretty much we during the 2 stages that we have, we close the pore pressure sensor, the pore pressure source, and also the volumetric change the valve right here to prevent the water to come out. So pretty much, if we do this, if we close this valve over here, pretty much we don't allow the drainage to happen. So that's why this is called an undrained test. So these two, the pore pressure and the volumetric change setup right here is kind of like belongs to the is preparing for the further advanced tests that are supposed to be covered at graduate level. But this is the whole picture, the whole setup of a triaxial device. And last but not least, we will provide for sigma 1 and sigma 3, like we'll lower it like vertically. So the unconfined compression test, we have a sigma 1 in the vertical directions. We realize the sigma 3, we have a sigma 3 inside the cell. So when we pressurize the whole thing, we have a sigma 3 like pointing up, and we apply a sigma 1 going down. So at the end of the day, if we put a low cell right here, what we are measuring is the deviated stress, which is sigma 1 minus sigma 3. So that's the two stages for this test. First, we do a consolidation test, which we apply like a vertical loading on it, and then that's the consolidation stage for this triaxial setup that can handle. But for the UU test, we will skip the consolidation test. So once we mark the soil samples, we will start the shearing stage. So once the soil sample is in place, with all this valve being closed here, when we start loading our soil samples, we will get the stress strain curve. So depending on what type of like a soil specimen we have, you have compacted soil samples or very sensitive, in other words, there's like highly over consolidated soils versus like a normally consolidated soils. We will have different type of stress strain curve. So and since we plug or we close the valve for the pore pressure measurements right there, we don't have any pore pressure measurements. But for the advanced triaxial test, we will have it. But for the UU test, pretty much we will only get the stress strain curve in total stress space. So knowing the stress strain curve is not enough. One more time, we need to handle this in the Mohr circle space. So with a Mohr circle space, we know the sigma 3. So the sigma 3 now is not 0 because it is a confinement test. We apply a sigma 3, which is like through the cell pressure into our into a triaxial device. So for example, if you allow like 100 kilopascal of cell pressure, then your sigma 3 will be equals to 100 kilopascal. And then after you apply the cell pressure, you conduct the triaxial test, the consolidated undrained test, you will get the stress strain curve. And from a stress strain curve, you know the maximum deviated stress, and then you correct that, or you find out your sigma 3 is a constant, then you can calculate the sigma 1. And from the maximum stress that you have, then you have the sigma 1 maximum. Then you can plot out the Mohr circles to represent the failure conditions of the soil samples. So with that, we can form a Mohr circles, sigma 3 and sigma 1 max. But realize that the difference between the UU test and CU test is the sigma 3 is not 0. And the radius of the Mohr circles tells you the undrained shear strength, SW.
Okay, let's look at the details of consolidated undrained test. So let's see the whole story from initially when a piece of soil elements or soil samples is in the ground at the in situ conditions, then sample it, and then go to the lab, or when you just proceed to specimens in the triaxial setups, to the end when we start to shear the soil samples. So firstly, when a piece of soil elements or soil specimens in the ground, it has total stress sigma naught on it, and also it has the initial pore pressure. We can also calculate the effective stress, which is the difference between the total stress and also the pore pressure. Then we start to sample these soil specimens. We we mobilize drill rigs and then using Sharpie tubes to collect the soil samples. And then when the soil samples is removed to the ground surface, and now the confining stress provided by the ground that used to be there now are all gone. So the sample stress, the total sample stress becomes zero. But like you realize that for clay samples, even though we remove all the confining stress, a clay sample still can being cohesive and holding itself. And it is because there's a suction force provided as a pore pressure to keep the samples intact. And that is because we assume all the original vertical stress now become a negative pore pressure that able to hold the samples together. And we also assume there's a no disturbance from the sampling, which means the soil samples has no change in volumes and no change in the moisture during the sampling process. If that is true, then we can assume all the effective stress, initial effective stress become the negative pore pressure. So this is an assumption, and this may not be perfect because we know there's a soil disturbance, and also depends on the quality of the drillings. To some degree, it's not all the stresses, effective stresses, become a negative pore pressure holding the samples together to some degree of the disturbance that we don't know. But to understand what's going on, or for this UU test to be work, we assume the whole thing is no disturbance, which means all the initial vertical effective stress become the negative pore pressure to hold the samples together. So this is an assumption. And since we know the pore pressure and also we know the total stress, so we can calculate the effective stress. So the effective stress during samplings at no disturbance, it will be equals to the total stress minus the pore pressure, and then now the effective stress at samplings go back to equals to the initial stress in situ. So this works. So the next stage is we have the soil samples and then we mount it on a triaxial setup. And through the triaxial setup, it has a pressure chamber, so we can apply a cell pressure, sigma C, total stress on it. And we can update the pore pressure. So the pore pressure from sampling is negative of the sigma pi naught, and then now we add the cell pressure on that. So now we have the new pore pressure at samplings. And we can calculate the effective stress too. So the effective stress in the triaxial setup will be the total stress minus the pore pressure, and the pore pressure is equals to the negative of initial stress plus the applied cell pressure. So if we do a math, the soil samples, the stress state at the effective stress state in triaxial setup is still go back to in situ conditions. So with a key assumptions over there, there's no disturbance. The UU test work in a way that the soil samples in the triaxial setup before we start the shearing stage is still same as the stress state in situ, the effective stress in situ, sigma pi naught. Since this is an unconsolidated undrained test, so we don't have the consolidation stage. The consolidated stage pretty much will be for the advanced test that we discussed in the previous slide. So we don't have the consolidation stage. So at the soil samples now, under the applied cell pressure, is ready to shear. So during the shearing stage, we will apply the deviated stress, and then now we can find our sigma 1, and then we can plot out this sigma 1 versus a axial strain curve. So this slide here is involves some advanced concept in geotechnical engineering. So if you need more help if you want to know more about this, so you want to have more in-depth study about the sampling process and how the whole thing works, feel free to go to my office hour. I will be happy to discuss more with you. And also this test, since this is a usual test that we don't measure the pore pressure, and also this test is only able for us to do our total stress measurements. So there's no effective stress measurements. So one more time, so if you need more help on this topic, feel free to come to my, particularly on this slide, please come to my office hour. So furthermore, when we talk about the Mohr Coulomb failure envelope, so this equations is the one that we know, and then since last lecture, and also we have seen this Mohr Coulomb failure envelope from the direct shear test too. And in fact, for the case that when we have pure clay material, now all the strength come from cohesions. So the friction angles for clay is equals to 0, and then the Mohr Coulombs now will become a flat horizontal line, because now the strength will be highly depends on the cohesions. For pure sand, there will be another extreme. So in this case, all the strength come from the frictional force between the grains sliding against each other. So there's no cohesions for sand. For that case, then our failure envelope becomes a straight line that with a slope of a tangent 3 point, and there will be no y-intercept because cohesion is equal to 0. So more calculations are more relationship between different parameters, and we will do this through the Mohr Coulombs. So imagine it's one more time, we have solid elements that we know we are under a stress state of sigma pi 1 and sigma pi 3, and it has a failure plane that with an angle alpha right there. And we can plot out the explicit solid elements in a Mohr circle. So we can plot out all the stress and also the orientations of the plane in a Mohr circles. So if we know sigma 1 and if we know sigma 3, then we can plot out the Mohr circles. And one more time, we can find out the pole. In this case, the poles is a sigma 3, as we discussed it in the previous slides. So we know the pole, and then we know the orientation angle. So we can find out the stress state on this plane, which is the sigma alpha and tau alpha. So sigma alpha and tau alpha will be this intersection point over there. We know the pole, we know the orientations, which is alpha. Then we can find out the stress state. So now we are interested in to study the relationship between the failure plane angle alpha and the solid friction angle phi. So we through trigonometry we want to relate angle alpha and angle phi right there. So these are the failure plane, and on the Mohr circles, and this black line here from the line that has slope of the phi angles, and also the cohesions right there, and touching at the Mohr circles, that is our Mohr Coulomb. So if we look at the triangle right here, BC, and the triangle like a BCD, we look at the radius of BC and CD, they are the same because they both are the radius of the circles. And if we also look at the angle CBD and also angle DB right there, both of them are the same because they are also the same angle alpha, with the conditions that we're looking at, and isotropic triangles have the same length, being the radius of the circles. We also know angle ABC is a right angle because it's a tangent line touching the circle. With that, we can calculate at angle CBA right there. So we know this angle, which is 90 minus phi. So if we go back to the triangles of B, C, D, by summing of all the angles, we get the angle sum of 180 degree. So now we get the equations that is in terms of both alpha and phi. So we can solve for alpha in terms of angle phi. So we got these equations, which may help us in the future for analysis when we look for friction angles given the failure plane, or the other way around, like we are given the the alpha angle, but we solve for the phi angle. So furthermore, we try to look at for another relationships. We try to look for how the phi angle can relate to sigma 1 and sigma 3, maybe particular at failure conditions. So this is very useful. So one more time, it's like we have a piece of solid elements. We know sigma 1 and sigma 3, and also induces the shear plane with angle alpha. In the Mohr Coulomb's envelopes, or the Mohr Coulomb circles, we can plot out. We know sigma 1 and sigma 3. We can plot the Mohr circles, and we also know the Mohr Coulomb failure envelope, which is the black line right here, with interceptions of c pi, one intersection c pi's, and also a slope of phi angle. And also we know the failure plane with an angle alpha that like going through the pole and also touching the failure point. So if we, in this triangle, if we look at a triangle ABC, so the goal here one more time is through like this trigonometry for this figure here, we try to relate angle phi with sigma 1 and sigma 3, which could be quite like powerful, because once you know, if we're able to do it, so which means once we know sigma 1 and sigma 3, then we can calculate the friction angle, or the other way around. So back to this diagram now. So if we have, if we go look at triangle ABC, we look at the sine theta, or sine phi, right? Sorry, sine phi right there will be equals to the radius of the circles divided by the distance right here. We call it d. The distance of AC, we call it d. And what is this distance d actually equals to? It will be equals to from the point A to the origin points, which is, if we look at this triangle right there, this part will be c times cotangents of phi. So if you go home, try to work out this trigonometry, you will find out like this part here is c times cotangent phi pi. And from the origins to the center, it is represent the stress state. We now require like sigma pi center. And further develops, if we try to express the radius of the circles and also the coordinates of the this center stress sigma right there, we can express them in terms of sigma 1 and sigma 3. So now with these equations, we can express the angle phi point in terms of the cohesions in sigma 1 and sigma 3. Is getting to where we want to get to. And for the case that you are working on sand, we know that for sand, there's no cohesions. So the cohesion terms will drop out. And we come up with formulas, what we call these obliquities relations, for us to find out the sine phi points in terms of both sigma 1 and sigma 3. So which in other ways, like we look at this as once we know about sigma 1 and sigma 3, we can calculate the friction angle for sand, because like we are for sand, the cohesion drop out. So let's do a quick examples. So that's a triaxial test will perform on clayey soils under UU test conditions and consolidated undrained conditions. Now you're asking you to find the cohesions of the soil and if the major and minor stress at failures were measured. So to solve a question like this, it's always good to start with the Mohr circles to help you to visualize the whole thing. So on the Mohr circles, we know the major minor stresses of failure, which means we know the sigma 1 and sigma 3. So if we know sigma 1 and sigma 3, then we can plot out the Mohr circles. And the questions here being asked are the cohesions. Then we know the cohesions pretty much is the strength for the clay samples, which is the maximum shear stress, which is the radius here we talk about. So the cohesions for this clay samples will be 96 kilopascal, and it can be solved through Mohr circles. Okay, next examples. This one can be fun. So in the beach, like you wonder like how tall can a sandcastle be constructed, given all the geotechnical parameters. So for example, now you have a sand that you work on. You know the friction angle that is like a 33 degree, and also you know the unit weight of the sand is 17 kilonewtons per meter cube. So the sandcastle is like is subjected to a sigma 3 point and sigma 1 point. And with that, like, you know, you want to calculate how tall it can be. And also we is given the information that the sand is unsaturated, which means it has a negative pore pressure of 2 kilopascal. So with the negative pore pressure, and also you know that the sigma 3 is total stress is equal to 0. So this kind of like reinforce the concept of sampling we talked about in the previous slides. Because like now the sandcastle is sitting above the ground, and you are not applying a cell pressure, nor like, you know, underneath the ground that like you have soils that are adjacent to it to provide the confining stress. So nothing is confining it. So the sigma 3 is equal to 0, is total stress. But for the effective stress, you have some pressure or you have some stress to hold the sandcastle together, and it comes from the negative pore pressure. So if you calculate the effective stress, you know the total stress and you know the pore pressure. So the effective stress in the horizontal directions, or like, you know, all around, is 2 kilopascal. Then like we make use of what we just learned, the oblique critics like relationships. We can relate the friction angles with sigma 1 and sigma 3 points. So we know sigma 3, and also we know like a 3 point. Then we try to back calculate what is sigma 1. So we plug in sigma 3 and also 3 point. We find out sigma 1 point is 6.78 kilopascal, and that is in effective stress. And we calculate the total stress. So we're adding the pore pressure back to this vertical effective stress. Then we can find out the vertical stress, sigma 1. So the sigma 1 vertical stress that holding the samples together is 4.78 kilopascal. And we know the total stress is equals to the unit weight of soil times the height. So we know the unit weight, we know sigma 1. With that, we can back calculate the height of the sandcastle is 28 centimeters.